So let's talk a little bit first about linear versus nonlinear systems. A system is said to be linear if it follows the superposition rule. So if I have a given system, shown here by these boxes, if I put in x1 and I get out y1, and then I put in x2 and I get y2, the system's said to be linear if I can superpose x1 and x2 and get out a superposition of the output. So if I have ax1 plus bx2, I get ay1 plus by2. So you can see that A gives me A, and I can also put in two inputs, and I just get out the two outputs that are there. The basic way to check is this idea of linearity. If I put in one input, and the example I usually use is I just double the input, do I get double the output out? If the answer is yes, it's linear. Now if you notice, just as an example, if I have an amplifier that the output equals m times x plus b, where x is the input, right? You'll notice if I put in 2x, I'm going to get m times 2x plus b. If I put in 1x, I'm just going to get mx plus b. And what you'll notice is this second one is not twice the first one. So a system with an offset in general is not linear, even though we think about the gain in both of these examples, m is being linear. So really the superposition is a good way to check if you actually have a linear system. You should get twice the output if you put in twice the input. A system which is not linear, not surprisingly, is called nonlinear. All right, so let's take a look at an example. So here I have on the left a single tone coming in, A cosine omega 1 t. And if I have a linear amplifier with linear gain G, this means G is just a constant. Then on the output, I get the same frequencies, and they're just a bit more increased in power relative to the gain. I'll just make one side comment when we talk about amplifiers. We need to be careful. Here we're talking about a voltage going in, so the output is a voltage. Sometimes we'll talk about amplifiers as a power going in and a power coming out. So you always need to make sure you know whether you have a voltage gain or a power gain. Typically, when we're talking about signals and voltages, we're always talking about a voltage gain. All right, now if this is a linear system, then I can put two inputs in, A and B cosine, at two different frequencies, and I should get out just G times both of those. So both inputs are amplified by the same amount, and I don't have any additional frequencies. Now a nonlinear system would be one where I put in two tones, A prime and B prime, and I get out the same two frequency components, but they may not have the same coefficients, and I may also have additional frequency components. So you can see here that the different tones could be amplified differently. We get newer frequencies than we had before, and this is what happens with a nonlinear system, and typically happens when the gain has some dependence on the input. And we're going to talk a lot about that with intermodulation coming forward, about the generation of these additional products and how they cause us difficulties. So you need to always check, because most systems in the real world are nonlinear. However, we just simplify them as linear systems, but usually there's some caveats or conditions in which they're linear. So maybe it's the input level, the bias, the load impedance. So whenever you assume a system's linear, make sure you know what parameters that is valid for. And remember that almost every real system is nonlinear. And the basic example that I use is any amplifier cannot amplify the signal larger than its supply rails. So almost every amplifier saturates, and that's one of the most common types of nonlinearity. And once again, always check and make sure the conditions for your linear assumption are met. Okay, so why and how do we want to model nonlinearity? First off, some nonlinearities have physical origins, so building a model for them can help us understand the physics behind them. And the second part is that if we want to analyze and use a computer to simulate these nonlinear physical phenomena, we need some type of model for them to do that. So it's good to have a model for both reasons of explaining physical origin and also for modeling these nonlinear physical phenomena. So in this course and almost everywhere, we use a Taylor series for modeling nonlinearities. And you probably remember this. We write the output in terms of the inputs, right? And they have these coefficients alpha 1, alpha 2, alpha 3, where they're given here. And if you recall from math class, they're just the first partial derivative, second, and third. That we usually all remember. The part we forget is these partial derivatives are all taken at a bias point. And so I'll just draw an example here. If I have a nonlinear function that looks like this, and I want to calculate alpha 1, I need to know where I want to calculate these partial derivatives at. And oftentimes we'll pick 0, but not always, and then we'll find the slope at 0. But just remember you need to figure out where the bias point is to calculate these coefficients. And the accuracy of the model is usually limited by the range of the input level. As the inputs get higher, we need to count on more and more terms. So let's look at an example. RF amplifiers and many amplifiers usually exhibit a nonlinear behavior for large input signals. So I've given an example here below where this is an amplifier with a gain G. And you can see it saturates, and it has a quasi-linear relationship in the center here. And by the way, G would be negative in this example. So when I put in a positive V in, I get a negative V out, so the inverting amplifier. So we're going to approximate this expression using a Taylor series. One thing that we need to figure out is how much of Vn do we really want to model? And that'll tell us how many terms we need to go. So let's just look at a linear approximation. And like I showed before, I can model just with alpha 1. Sorry about that. This is alpha 1 here. I can model that with one coefficient, and I do my partial derivative around 0 here. And then if I want to start to model some of the nonlinearity, I can start adding terms. I can add a cubic term, and I get a little bit of this curve and a little bit of that curve. Sorry. And then I can go forward and I can add a fifth term, and you can see now I get a little bit of this curve coming down here. You may have noticed that we have all odd powers of the input voltage, and that's because we have an odd function here. So we're going to have 3, 5, 7, 9, and so forth. And we can add more and more, but if you notice, we've gone out to about here with 3 terms and have done very well. By the way, notice 3 terms does not mean to the power of 3. The third term in this example is to the 5th power. But if I wanted to actually model this, it's quite a departure, and I'm going to need more and more terms to take out to model my saturation.